let G be a group, and let H be a subgroup of G, and let G apply. That's one my forwards. Let G be a group, let H be a subgroup of G, and let G act by left multiplication on the set A of the left cosets of H in G. Let G be a group, let H be a subgroup of G, and let G act by left multiplication on the set A of left cosets of H in G. Let by H be the associated permutation with blah blah blah. The kernel of the action is blah. Let G be a group, let H be a subgroup of G, and G acts by left set of left cosets of H in G. Pi H be associated permutation with permutation. Then G acts transitively on A. Okay, yeah, because if I have G, H, and G tilde H, then all I have to do is consider G tilde, G inverse acting on the side GH is equal to GH. So, transitively, stabilizer of G in the point of the point 1H is a subgroup of H. Okay, means for what G? GH is equal to the things in G, which G times H is equal to H, which is equal to H. So now the last part, the kernel of the action. What's the kernel? The kernel IH is equal to the things in G for which IHG is equal is the identity, which means that for all G x H, G x H is equal to x H for all SH in A, which means that G, P is a prime and P is a group of prime power order P alpha, for some alpha greater than 1, then P has some non-trivial center. Okay, oh there you go. If the power of P is over P squared for some prime P, then P is a billion. More precisely, P is isomorphic to either a cyclic group of order P squared or ZP times ZP, blah blah blah. Sure, why not? What's G quotient the centralizer of something? What's G quotient the centralizer of something? What's G quotient? Oh, it's the known what? Conjugation. Conjugating again. If H is a normal subgroup, then if I consider conjugation on H by group G, then what is the kernel of the action? The kernel of the permutation representation is the centralizer of H. Yeah, okay. So the centralizer of H is whatever. Oh, okay. It's just first isomorphism theorem again. Okay, let H be the normal subgroup of G, and then I consider for each H, G dot H is equal to for each G for each G, H gets mapped to G H for all H in H. Sure. Then consider it's mapped from since conjugation is an automorphism, instead of SH, can consider this is trivial. Then kernel of is equal to, okay, so G is in G where what are we doing now? We are taking conjugation. So if the things in the kernel are the things that don't change, that don't change the things. Okay, G is acting on H, that such that H is equal to G, H, yeah, G, that G dot H is equal to H. It's acting on cosets. What are we acting on? We are acting on elements of H. Okay, we are acting on elements of H. So G dot H is equal to H for all H in H. Goes to G. H is equal to H for all H in H is equal to G in G. It's just C, G, H. So G should C H is isomorphic to this G, which is C. And then we call this now H. Fuck you. Why? What? Oh. G has no proper subgroup H of index less than 5. G has no subgroup, no proper subgroup of index less than 5. Why? If it's 1, then it's not proper. If it's 2, 3, 4. No proper subgroup H of index less than. If G then, by theorem 3, G would have a normal subgroup K contained within H, which with G quotient K isomorphic to some subgroup of S4, S3, or S2. If G has a proper subgroup H of index less than 5, then what are we considering? We are considering left multiplication. Okay. So, what's the permutation? Okay. G quotient what? Okay. What are we quotient? Oh, we're quotienting with. Are we quotienting with H itself? Oh my god, am I stupid? Because what? Wait. G quotient K. If H were a subgroup of index 4, 3, or 2, then G would have a normal subgroup K contained within H, with G quotient K isomorphic to some subgroup of. Consider, okay. Why? Consider G acting on H. Are we acting on H or cosets of H? Am I stupid? Oh no. Am I stupid? No way. No way. Oh no. Yeah, we're acting on cosets. Acting on cosets of H. Okay? By left multiplication. Because what is it trying to, what did it say? It said that, it just said that curve PH. Okay, so PH, why am I saying P? Am I retarded? Oh my god, oh no, I'm stupid. Pi H, what does pi H do? Pi H takes G and takes it to, it is a permutation on the cosets of H. Okay, but, sure. Okay, each G sort of like shuffles the cosets of H, okay? So we are acting by left multiplication on cosets of H. Then what now? I'm considering the kernel, because the kernel gives us a free normal subgroup of what? The kernel gives you a subgroup for this, the kernel, which is necessarily a subgroup of H as well. Because what?
because we have to fix H. Okay, this is because we have to fix H. Because if it fixes everything, then it fixes H. And the things that fix H are in H. Wow. Shocking, shocking, shocking revelation. Wow, so insightful. Okay. G. What now? So if we have the index be 2, 3, or 4, then we have a permutation from G to S4. Okay. S4 would have a normal subgroup K contained within H with G quotient K isomorphic to some subgroup A, S4, S3, or S2. Okay. Yeah, exactly. It's so simple. Okay. So then there exists K, which is actually the kernel of the permutation representation, which is actually a subgroup of either S2, S3, S4. Okay, what's the problem with this? Why can't this exist with K actually? What is this? No, is it kernel? No, it's not a kernel. It is G quotient the kernel. There's the first isomorphism. Oh, there's the first isomorphism. G quotient K is isomorphic to IHG, which is a subgroup of that, where K is normal in G and K is a subgroup of H. So, okay, what are we doing? We are taking a group. We have group G and we have a subgroup H. And we are considering left multiplication on cosets of the subgroup. And so we ask ourselves this question. Okay, it is transitive, that's simple. Okay, the fact that it's transitive is simple. Just write it out, yeah? Just do it. Then what else? We want what stabilizes the subgroup itself? The things that stabilize the subgroup itself are elements such that when you multiply, when you left multiply the subgroup, you get back the subgroup. So it is just elements in the subgroup. It is precisely the elements in the subgroup. So the stabilizer of H is H. Cool. Wow, so insightful. But now we consider the permutation representation. So G left multiplying the cosets of H is sort of like shuffling the left cosets. Yeah? So like it's shuffling them. So it corresponds to an element in naturally corresponds to very naturally, to some element in like a symmetric group of what? The number of orders, the number of cosets of H. So the symmetric group of the index of H in G. Wow, so nice. Okay, it corresponds to some shuffling. Yeah? And how do we word that? So what is in our kernel? The kernel consists of the elements in G such that when I multiply any left coset of H, I get back the left coset of H. So it is the elements G such that GXH is equal to H for all X. GXH is equal to XH for all X. That means that X inverse GX is in H, which means that G is in XH, X inverse. For all X, so it's an intersection of XH, X inverse, where X comes from G, okay? That's it. So that, what is that? That is the kernel of the permutation representation. Okay? Okay, so that's like what it is like concretely, but what is it used for? If you let K be the kernel, okay? Then what does the first isomorphism theorem tell you? It tells you that if I take a homomorphism, yeah, so G quotient K, which is the kernel, is isomorphic to the image of the homomorphism, which is just some subgroup of the symmetric group of, well, the number of cosets of H. So what if I take H to be itself? No, do I take H to be itself? No, do I take H to be G? What do I take H to be? I take H to be G itself, then it is, then G is then the kernel is if I take H to be G, then our kernel would be the elements such that G X is equal to X for all X. That means that necessarily G is equal to the identity. So the kernel is just the identity. Yeah, okay. So G quotient, the kernel, is isomorphic to G, which is isomorphic to some subgroup of the symmetric group consisting of the symmetric group of order G. Not, well, okay. Computing G, the order G elements, okay. Then, yeah, that's it. So every group is a subgroup of the symmetric group with like not order. I mean, yeah. It's a subgroup of SG, I guess. Okay, and that's it. That's it. It's so simple. It's actually so simple. Yo, simple. That's where you don't have a non-trivial normal subgroup. That's crazy.
since k is not equal to g, we have, okay, so k is a normal subgroup. We have k is a normal subgroup, but we said that g is simple. We said that g is simple. This is cause for concern. This is cause for concern. Because we said, what did we say? We said that g is simple. G is simple. So if g is simple, so either k is 1 or g. So k is equal to 1 or g. K is equal to g. Can k be g? Can k be g? No. Why? K is not equal to g because k is a subgroup of h, which is a proper subgroup of g. So k is a proper subgroup of g. So k is equal to g. So k is forced to be 1. K is forced to be 1. Okay. What's the problem with that? What's the problem with that? The problem with that is 60 does not divide 4 factorial. Since k is not, so k is equal to 1. This is impossible because 60 does not divide 4 factorial. Okay. Impossible. Why? Yes. Why? Because what is k? K is the things that map all the cosets back to itself. And all the cosets back to themselves. Why is k equals 1 impossible? Why? It's something about divisibility. Something about divisibility. The order of g does not divide 4 factorial. 432. We have that g, we have that g, okay, is isomorphic to g, is isomorphic to IHG, which is S2, S3, S4. This is of order 60, g is of 60, and this is of order S2 equals 2, S3 equals to 6, S4 equals to 4 factorial 4. So no g is not equal to some IHG is S2, S3, no. So we have no hence no proper subgroup of H of G less than
that because G is simple, the kernel is either too small or too big, It's either too small or too big. Because the kernel is normal, if the kernel is the entire group, then because the kernel is a subgroup of H and H is proper, then we have a contradiction where K is equal to G, but K is a proper subgroup of G. So that cannot be the case. If K is equal to 1, then we have that the kernel is equal to 1. Okay, the kernel is equal to 1. So the first isomorphism theorem tells you that G quotient K is some subgroup of either S2, S3 or S4. But because K is 1, G quotient K is isomorphic to G. So G is isomorphic to some subgroup of S2, S3 or S4. But G has 60 elements. S2, S3 and S4 are too small. You cannot contain G. G cannot be a subset of this initial group. So, okay. this give us? Give that. Hence, n2 is not equal to 3.
N2 is not equal to 3. What if N2 is equal to 5? N2 is equal to 5. Then consider, what do we consider? We are considering the subgroup. Okay, let's considering, what are we considering? What are we considering? Cosets. This is the number of cosets, right? Is it the number of cosets? I don't think so. Oh no. Oh. N has index 5. N has index 5. So the action of G by left multiplication on the set of left cosets of N gives a, oh wait, what? Am I stupid? No, I'm not. G, okay, because it's equal to the number of cosets of N, okay, the number of cosets of N. N is the normalizer, okay, we're not working with P, we're not working with the normalizer of P, okay, the normalizer of P. We're working with the normalizer of P, okay. Then consider the action of left multiplying. Action of left multiplying on, what we're multiplying? We're multiplying on n by g. On n by g. Okay. We have a permutation representation from g. And so how many cosets do we have? We have 5. Okay, so we have 5. So we take as 5. Because we are permuting 5 cosets. We're permuting 5 cosets. Okay? We're permuting 5 cosets. Okay, what about it? 5 factorial, what's 5 factorial? 120. Yo, that's crazy. 5 factorial is actually 120, which is crazily divisible by 60. That's crazy. That's actually crazy. Whoa. So what is the kernel of pi h? K is the kernel of pi h. Then what happens is K is a normal subgroup of G and K is a subgroup of N. No, yeah, where we are? Pn. Pn. What? Pi n. Pi n. Pi n. Pi n. Okay. Then what happens? K is a normal subgroup of G. So either K is equal to 1 or G. Is it 1 or G? It is not G. K is not G. Why? Because if K were G, then K is a normal subgroup of, okay, if K were G, then G is N, then necessarily N is equal to G, but G N equals to 5 is not equal to 1. So that means that K is equal to 1 again, right? Because I'm not like stupid. Kernel is 1. Okay, the kernel is 1. So G is isomorphic to G quotient K, which is isomorphic to pi n G, which is a subgroup of S5. G is isomorphic. So yeah, okay. G is isomorphic to some subgroup of identifying G with its isomorphic copy. We write previously. G is a subgroup S5. Sure. Then, if G is not contained in A5, if G is not contained within A5, then S5 is equal to GA5. No, wait, what? If G is not contained within A5, then S5 is equal to GA5. And by the second isomorphism theorem, A5 and G is of index 2 in G. Suppose if G is not contained within A5, then S5 equals to GA5. S5 equals to GA5. Why? S5 is This exercise classifies a group of order 60. There are 13 isomorphism types. Let G be an order. Let P be a CELO 5 subgroup of G, and let Q be a CELO 3. Prove that if P is not normal in G, then G is isomorphic to A5. It's if number of 5. Oh, what the hell? Oh, what the hell? What the hell? What the helly? What the helly? What the helly? What the hell? What the hell? What the helly? No, bruh. You're stupid. You're stupid. So I'm not the most stupid person because there are people that are more stupid. Oof. But people become less stupid. Oh no. People become less stupid. That's crazy. People become less stupid. And now I become more stupid relative to other people. That's crazy. What the hell? If G is not contained in A5, then S5 is equal to GA5. Oh, because why? Because oh fuck something. Because there exists G in G not A5, then GA5 is equal to G, I don't know. Let's say an A. Okay, so it's GH and G and GH is in A5. It's equal to, and so of course A5 is in here, but also, but consider AH where H is in A5 is equal to A5 is equal to S5 not A5. Because that's just everything, whatever. Algebra 1 is in GA5. So GA5 is equal to S5. Okay, I'm not stupid. Oh, that's crazy. So, what now? So, if not contained within A5, then S5. Okay, what's the problem with this? What's the problem? What is the problem? What is the problem? What is the problem? The problem is that G has no okay. I saw so we have G, and we have GA5, and we also have A5 here, which is equal to S5. Here we have G is an A5, and do we have that G is within the normalizer of A5? Do we have this? No. Do we have this? G normalizes. No. Why? J, and by the second isomorphism, A5 and G is index 2 in G. Huh? What? How? GA5, S5, S5, oh, okay. So like G and G and A is equal to, oh, it's here, right? It's, okay, whatever. I mean, S5, A5 is equal to 2. Which part is the one where you can take normal subgroups? And which is the part where you can only think about indices? Isomorphism. I'm actually so stupid. Like, I'm going through this shit so like slowly. I'll be dead before I finish this fucking book, bro. I'm actually so stupid. Oh. Let G be a group and H and K be normal subgroups and whatnot. Oh, that's the third one. Oh, I'm actually stupid. Let G be a group and A and B be subgroups of G and assume A is in the normalizer of B, and then AB is a subgroup of G. B is the normal subgroup of AB. B is the normal subgroup of A. So that's the part where you think normal, index, or whatever, blah. But how is G? How is G a normal subgroup of the normalizer of A5? How is G a normal subgroup of the normalizer of A5? That's crazy. No, it's not a normal subgroup, it's a subgroup. It's a subgroup. A subgroup of this. Okay. How is it G? What's the normalizer of A5? The normalizer of A5. Oh, because the normalizer of A5 is nothing because A, that's 5. That's crazy. Yo, that's crazy. Is it? Is it no? No, wait. No, it's not. But, is it A5? Or is it S5? I think an odd thing. Yeah, it is. It's equal to, yeah, it's equal to S5. Because the idea is that if I take any even permutation, and before that, yeah, I just do like 2 up permutations. I mean, yeah, okay, sure. Wow, so clever. Wow. This is equal to S5, and yes, G is in fact, G
G is in fact a subgroup of S5. Whoa, what a shocker. That's crazy. G, okay. Okay, now the problem is that G and A5, G and A5. The index of G and A5 is 2 in G. So G and A5 is 2 with G and A5 a subgroup of G. So G and A5 is actually normal in G where what do we have? It is not where G and A5 is not equal to G. Since why is that not the case? It's because G is not contained within A5, so G and A5 is not equal to G and A5 is not equal to A5. A5 and A5 is really less than A5, which is equal to 60. So 60 is equal to G. Okay. Is equal. So and G and A5 is it equal to 1? No. Why is it not equal to 1? Is it equal to 1? A5 is equal to 1. That's not the case, is it? G intersect A5 is equal to 1. What is something that can be equal to 1? So index 2 in G. I'm actually quite stupid, yeah? I'm actually quite stupid. So G and A5 is normal in G where G and A5 has order 30. Oh, that's actually kind of crazy. So contradiction contradicts simplicity of G. Simplicity of G. Okay. So G is contained within. So G is contained within A5. Within A5. Oh, but then G has 60 elements. A5 has 60 elements. Wait, yeah, A5 has 60 elements. So yeah, G is in fact A5 as desired. Yo, that's crazy. Okay, so how did I prove
go. Oh no, we're not done yet. We're not done yet. Because we still have n is equal to 15. Oh. Oh, that sucks. Assume n2 is equal to 15. If for every pair of distinct 0,2 subgroups P and Q of G, P and Q is equal to 1, then the number of non-identity elements in 0,2 subgroups of G would be 4 minus 1 times 15. Why? Am I stupid? The number of non-identity elements in 0,2 subgroups of G, if for every pair of distinct 0,2 subgroups P and Q is equal to 1. 2, 2, 2. Okay. The number of non-identity elements in 0P2 subgroups, 0,2 subgroups, 0,2 subgroups. Okay, so what is the order? What's the order? It's 4 minus 1. Okay, why? Why is it 4 and not 2? How do we know it's 4 and not 2? Am I stupid? Oh, because it's 60. Because it's 60. And 60 is 2 squared times 3 times 5. That's crazy. Whoa, that's crazy. So what's a CeLO2 subgroup of G? A CeLO2 subgroup of G is a group of order 4. Yo, that's crazy. That's actually crazy. Oh. Okay. So the number of this non-identity elements in 0,2 subgroups of G will be 4 minus 1 times 15. Because we have 15 0,2 subgroups. 15 0,2 subgroups, each 0,2 subgroup admits 4 minus 1 distinct. Okay? Distinct order 2 elements. We have 45 order 2 elements. N5 is equal to 6. Why is N5 equal to 6? What the hell? Why is N5 equal to 6 now? Oh. How is N5 equal to 6 now? How is N5 equal to 6 now? If N5 is equal to 6, then do we not just have a G is simple? Oh, okay. We need to show that it's isomorphic to A5. Oh, we have, if N2 is 5, then it's isomorphic to A5. Oh, then there's a contradiction. Oh. If N2 is 15, if for every pair of distinct, but N5 is equal to 6. Okay, because what are the possible values for N5? N5 cannot be 1. Otherwise, the CeLO5 subgroup would be a normal subgroup. That's crazy. And then G is not simple. So N5 is not equal to 1. Can N5 be 6? N5 can be 6. Can N5 be... N5 has to divide 12. So 6 is the only possible value for N5. Okay. Oh.
Okay, so n6 is equal to n5 is equal to 6. So how many elements of order 5 do we have? We have that we have 6. How many? Okay, we have 6 0, 5 subgroups. Each 0, 5 subgroup gives you 4 distinct things. So 24 plus what? 15. 24 plus 15 times 3. 24 plus 45 is 69. That's crazy. That's crazy. That's actually crazy. There's too many things to fit in G. Too many things to fit in G. G does not have enough room for that many things. G does not have enough room. It's too small of a group. It's too small of a group. Oh, too small of a group. Oh. Note. So it means to see, means to check for n2 equals to 15. Note that n5 is not 1, otherwise p 05 is normal p so contradicts simplicity of G. Contradicts simplicity of G. Contradicts simplicity of G. Oh no. Okay. If so, what are our options? We have that n5 is congruent to 1 mod 5, and that n5 is divides 12. So necessarily n5 is equal to 16. So what do we have? What do we have? How many elements of order P? How many elements of order P? And any elements of order 2 of 2k? Consider each P of 0 to G is of P is equal to 4. So 2 cubed 60 is equal to 2 squared. 2 squared. That's crazy. That's crazy. So 15 and 2 times how many things in n2? Wait, we have p times n2 times 2 squared minus 1 is equal to 15 times 3 is equal to 45. How many elements of order 5? How many elements of order 5? Elements of order 5. 6, 5, n 5 times 5 minus 1 is equal to 6 times 4 is equal to 24. We have 69 elements. Too many to fit in. To fit in G. G is equal to 16. Contradiction. So n2 is not equal to 2. For normal G. For simple G, not normal G, for simple G. Simple G. stupid. If for every pair of the same zero P2 subgroups P and Q. Oh. If P and Q is equal to 1 from or P, Q in 0 to J. Oh.
there exists distinct CO2 subgroups P and Q, with P and Q be equal to 2. Let M be equal to NG. No. Distinct. So that consists distinct P, Q, and CO2G with this not equal to 1. We have, but also, so P and Q divides 4. Since P and Q is a subgroup of P or Q, so, but since PQ distinct, P and Q not equal, P and Q not equal to 2, so P and Q is equal to 2. Okay. What now? Let M be the normalizer of P and Q. Since P and Q are abelian, note P equals to Q equals to 4 are abelian. This 4 equals to 2, so either 4 or both abelian. Z4 or Z2 cross Z2, both abelian. So since they are both abelian, P and Q is also abelian. It's also abelian. Okay, and what else? P and Q are subgroups of M. And since, okay, P and Q subgroup of M. Why? Because P is a subgroup of M. Why? Because if any P in here, Q be in P and Q. Okay, let P in here. Then P and Q. Yeah, it's equal to this because it's abelian. Because it's abelian. So Q, both are subgroups of this. So what next? P and Q are subgroups of M. And since G is simple, M is not equal to G. P is a subgroup of M. So since P is simple, since G is simple, and the normalizer of P and Q is not equal to G, otherwise P and Q would be a normal subgroup of G. Okay. I.e. divides m. 4 divides m. 4 divides m. Plus 4 divides m. Why? 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 Because P has 4 things. Oh, because P 4 and P, yeah, so P and P, so yeah, P divides M, 4 divides M, okay, 4 divides M, yeah, and so M. Otherwise, P equals to M is equal to Q. So M is strictly greater than 4. Greater than 4. So the only remaining possibility is M is equal to 12. No other because we need to G1 is equal to, okay, if you're naive, what we could have 4, we have 20, that will be 3, which is less than 5. Which cannot be the case, which cannot be the case, okay, which cannot be the case. Okay. Then, 1. If M is equal to G, okay, thus 4 divides M. Okay, but now the argument, okay, then we can now replace previous N. What was our previous N? Our previous N was what? This is so crazy. What? If G is a group of order, if G is a simple group of order 60, then it is isomorphic to A5. Why? Why is that the case? Let G be a simple group of order 60. So N2 is equal to 3, 5, or 15. And let P, okay, N2 is equal to 3, 5, or 15. Why? Because N2 cannot be 1. N2 cannot be 1 because if N2 is equal to 1, then you have a CELO2 subgroup which is normal. So G is not simple. So N2 is congruent to 1, not 2. So, and it is, and N2 divides 15. N2 divides 15. So it is an odd number that divides 15, which is 3, 5, or 15. 3, 5, or 15. So what if N2 is equal to 3? Suppose we have a proper subgroup with index less than 5. So 2, 3, or 4. Not 1 because then that would not be a proper subgroup. If you have 2, 3, or 4, then we consider the permutation representation. Okay. Consider the kernel. Okay, wait, no. Consider G acting on H, the cosets of H. A proper, okay, what's this? Let H be a proper subgroup of G. Okay? H is a proper subgroup of G. And then we let G act on the left cosets of H, on the cosets of H by left multiplication. Okay? Then we consider, what we consider? We consider the permutation representation. We map G onto permutations in S index of H in G. Okay? The S, the number of cosets of H. So it's either 2, 3, or 4. Now we have a kernel, the kernel of the homomorphism, which is a normal subgroup. In where? A normal subgroup in G. But we also have that H as a subgroup of the kernel. Why? Because the kernel consists of stuff that fixes all cosets. So the elements that fix all cosets are necessarily elements that fix H. And if you fix H, then you are in H. Okay? If you fix H, then you are in H. So the kernel is contained within H. Okay? So the kernel is contained within H. Okay, that makes sense. Does that matter? I don't know. Does it matter? Maybe not. Okay, we now have a normal subgroup K, which is the kernel of the homomorphism. Can K be the entire group? No. Why? Because K is a subgroup of a proper subgroup of G. So if K is equal to G, then it's a proper subgroup of G. G is the proper subgroup of G, that makes no sense. So K is not equal to G. So because G is simple, necessarily K is equal to 1. What happens if K goes to 1? That means that G is isomorphic to G quotient K. Yeah, G quotient K. But by first isomorphism theorem, what is G quotient K? G quotient K is equal to the image of the homomorphism, which is a subgroup of either S2, S3, or S4. But the problem is now that we have G is isomorphic to something in either S2, S3, or S4, which is simply too small to contain G. Yeah. So G cannot be isomorphic to some subgroup of any of these groups. S4 is of order 24. Okay, S4 is of order 24. So we cannot have a proper subgroup of G with index less than 5. Okay. So what do we have? So we have N2 not equal to 3. Because if N2 is equal to 3, what is N2? N2
is G, the index of the normalizer of A, CeLO 2 subgroup. Yeah. So it is the index of a proper subgroup. What is the proper subgroup? A CeLO 2 subgroup, any CeLO 2 subgroup. You take the index, and the index is 3, which is less than 5. Crazy insight. Yeah? Like 3 is less than 5. Yeah, that's crazy. So if n2 is not equal to 3, what about n2 equals to 5? If n2 equals to 5, what n2 equals to 5? What about n2 equals to 5? Again, we consider permutation. The permutation representation. So we have a homomorphism that takes G to how many cosets do you have? Now we have 5 cosets. So it is a homomorphism that takes G to S5. You go G to S5. Okay? G to S5. Cool. What about G to S5? G to S5. Again, hey, the kernel is normal in G. What else? The left cosets. Am I stupid? No, I'm not stupid. We are working with n. We are working with left co. We are working with cosets of n. We are working with cosets of n. Yeah. So how many cosets of n are there? There are 5. So we claim that the image of G in S5 is contained within A5. And so we first identify G to its image in S5. And we can do that because G is isomorphic to its image. Why? Why is it isomorphic to its image? Because k is equal to 1. Why is k equal to 1? Because k can only be, k is normal in G, k can only be 1 on G. Can k be G? No. Why? Why can k not be equal to G? Because k is a subgroup of n, where n is a proper subgroup of G. Okay? So then we have the same problem with G cannot be a proper subgroup of itself, so necessarily k equals to 1. So k equals to 1. We identify G with its image in S5. Okay. Identify G with its image in S5. G. So we claim that G is contained within A5. If it is not contained within A5, then there is something in G which is not in A5. And we can take that G and we can generate the remaining thing. So we consider G A5. Yeah? So G A5 is equal to S5. Because everything in S5 can be created with G A5. Yeah? Something in G A5. And the reason it can be done so is because the G contains something that is not in A5. So it's like a, odd permutation, even permutation type shit going on. Yeah? Odd permutation, even permutation. Sure, G equals to, okay, whatever. So where were we? We were that in that G is contained within A5. Okay, why is that the case? So S5 is equal to GA5. Okay, now comes the fun bit. The fun bit is that what is the normalizer of A5 in S5? It is equal to S5. Yeah, and that is where the permutation, odd permutation, odd permutation, even permutation shit comes in. But the normalizer of A5 in S5 is S5, and G is a subgroup of S5, so G is a subgroup of the normalizer of A5 in S5. So if we consider the diamond isomorphism theorem, second isomorphism theorem, the diamond. So we have G over here, G over here. A5 over here, where G is a subgroup of the normalizer of A5. G over here, A5, GA5 is equal to S5. GA5, G, A5, and G intersect A5. Now, what does the diamond tell us? It tells us that the index of G intersect A5 in G is equal to the index of A5 in GA5. Okay, so GA5, but GA5 is nothing but S5. So what is the index of A5 in S5? It is 2. Yeah, because you have the even permutations and the odd permutations. Wow, that's so insightful. You have even permutations and odd permutations. So the index of A5 in S5 is 2. So by the diamond, and the second isomorphism theorem, what does it tell us? It tells us that G intersect A5 is, the index of G intersect A5 and G is equal to 2. Okay, how is that helpful? How is that helpful? G intersect A5 is a subgroup. G intersect A5 is a subgroup of G. But now we know that it has index 2, so it is normal. G intersect A5 is a normal subgroup of G. Is it equal to 1? Is it equal to 1? Is it equal to 1? Okay, first things first, is it equal to G? Oh, no, it's not equal to G because there's not enough elements. It's only like, okay. No, am I stupid? No, no, it's not equal to G because A5. It's not, G is not contained within A5, so it's less than 60 elements. It has less than 60 elements. It is not equal to G, which has 60 elements. Okay, is equal to 1. Can it be equal to 1? G intersect A5 is equal to 1. No, because we need that G contains something which is not in A5. Am I stupid? Not contain. Am I stupid? Why is it not in 1 again? Oh, because the index. So what is the order of G intersect A5? Is 30. Is 30. Why? Because order G is 60. The index is 2. Okay, so the order of G intersect A5 is 30. Is 30. Okay. So, and then it is a normal subgroup. But that contradicts the simplicity. Okay, that's it. We have now constructed, supposedly, a normal subgroup of order 30. That cannot be the case. That's a contradiction. That contradicts the simplicity. So that means that G must be contained within S5. No, not S5. G must be contained within A5. So how many elements are there in G? 60. How many elements in A5? 60. So if G is contained within A5, then we have exhausted everything in A5, everything in G. G is isomorphic to A5. Wow, that's crazy. Okay, that's crazy. G is isomorphic to A5. But what if N2 is equal to 15? If we have a case where distinct CeLO 2 subgroups have intersect of order 1, which is that if we have distinct CeLO 2 subgroups intersect only at the identity, then we have too many elements. Why? Because then every CeLO 2 subgroup contributes 2 squared. 2 squared, is it 2 squared? Yeah, 2 squared minus 1 times how many CeLO 2 subgroups are there? There are 15. 15 times 4 minus 1. 15 times 4 minus 1. So that's 45. 45 elements, distinct elements of order 2 to some power. 2 to some power, either 2 or 4.
Either 2 or 4. 45 elements of order either 2 or 4. Now what about n5? n5 cannot be equal to 1, otherwise we have a normal 0, 5 subgroup. So n5 has to divide 12. n5 divides 12. n5 is congruent to 1, not 5. So n5 is equal to 6. And how many elements of order 5 are there? There are 6 times 5 minus 1, so 24. So 24 plus 45 equals to 69, which is greater than 60, cannot fit within our group G. So there exist 0, 2 subgroups with non-trivial intersection. So what about it? P and Q are subgroups of G. P and Q are subgroups of P. P intersect Q is a subgroup of P and it's also a subgroup of Q. Okay, so the order of P and Q is divides 4, but because they're distinct, it's not equal to 4, but now we are assuming that we have some which are not equal to 1. So necessarily, the ones that are not equal to 1 are equal to 2. Okay, are equal to 2. So now we have a P intersect Q, which is of order 2. So, okay, P and Q are both of order 4. P and Q are both of order 4. P and Q is of order 2. If you consider N to be the normalizer of P and Q, the normalizer of P intersect Q. What now? Normalizer. P is a subgroup of both P and Q have orders of the form P squared, which is equal to 4, which is 2 squared. So it is abelian. Why? Because it is isomorphic to either the secret group of order 4 or Z2 cross Z2. Okay, that's crazy. So P and Q both are abelian. So how does that help us? That helps us by showing that P is the subgroup of the normalizer of P and Q. Why? Because, well, P times the coset P times P and Q is equal to the right coset P and Q and P. Why? Because it's abelian and you can just shift shit around, like shift shit around. Yeah? So the left coset is equal to the right coset and whatnot. Okay. P is a subgroup of, did I call it M? P is a subgroup of M, Q is a subgroup of M. What now? How does that help? Okay, P is of order 4 and P is a subgroup of the normalizer of P and Q. So the normalizer, so 4 divides the normalizer. 4 divides the order of the normalizer. 4 divides the order of M. Can the order of M be 4? Why is it not? Oh, it cannot be 4, otherwise P and Q, P equals to M equals to Q. Am I stupid? No. Oh, no, I'm not. Because P is a normalizer. P is a subgroup of the normalizer. If the normalizer has order 4, then that means that P being order 4 in a subgroup of order 4 means that P is equal to M. But Q also has the same relation, so Q is also equal to M. Q equals to M equals to P, which contradicts the requirement that P and Q were distinct. Okay? So
m is not of order 4, m4 divides the order m is not of order 4, m is of order 4, strictly greater than 4. So what can m be? What can m be? M has to divide 16, and 4 has to divide the order of m. So we have 12, we have 20, and we have 60. Can it be 60? No. Why? Why can't it be 60? Because if it is 60, that means that m is equal to g. If m is equal to g, that means that p and q is normal. P and q is normal. P and q is a subgroup of order 2, which is normal, which is a contradiction. Can p and q be of order what were the choices again? 12 and 20. Can it be 20? No. Why can't it be 20? Because if the normalizer of if m is of order 20, then the index of m is 3. And we have shown that if you have a subgroup index 2, 3, and 4, then you do not have enough, g is too big, g is too big to fit within your symmetry group, yeah? G is too big. Okay, now what about if m is of order 12? If m is of order 12, then the index of m is 5. If m, you have 5. The index of order. So previously we worked with if the normalizer of a pseudo p subgroup is, if the index of a normalizer of a p subgroup is order 5. But now what we have is the index of the normalizer of the intersection of two subgroups. Okay, and then that is equal to 5. And so G would be isomorphic to A5. G would be isomorphic to A5. G is isomorphic to A5. This leads to a contradiction in this case because N2A5 is equal to 5. CF the exercises. Fuck me, bro. Fuck the exercises. Oh, okay, whatever. Okay, so then, okay, no, we're not done. We're not done. So, G is isomorphic to A5, but a contradiction because N2A5 is equal to 5, which is not equal to 15. So N2 is not equal to 15. So N2 is equal to 5 and C above. Oh. So the case where N5 is equal to 15 comes down to, hey, it should be, it somehow reduces to the case where N2 is equal to 5. Instead of looking at the normalizer of any P02 subgroup, we consider the intersection of two special CO2 subgroups with non-trivial intersection. And then come to a conclusion, come to a seeming conclusion that G is isomorphic to A5. But then there is a problem. The problem is that N2 in A5 is 5, but we have started off with N2 is equal to 15, so that's a contradiction. So we do not have that N2 is equal to 15. We do not have N2 is equal to 15. So the only remaining possibility is that N2 equals to 5 because that is the only coherent number. Yeah, that's the only possibility which gives coherence. You know, yeah. That's crazy. That's so crazy. Fuck. So much time. I'm really so stupid. You know? Spend so much time. It's just like this simple, that's not very simple shit, no? The simplicity of AN. There are a number of proofs of simplicity of AN where n is greater or equal to 5. The most elementary involves showing AN is generated by 3 cycles. Then, one shows that a normal subgroup must contain a 3 cycle and hence must contain all the 3 cycles, so cannot be a proper subgroup. We include a less computational approach. Note that A3 is an abelian simple group and that A4 is not simple. A4 is not simple. A3 is abelian simple, A4 is not simple. But then A5 is simple for n greater than equal to greater than or equal to 5. Why? Why? That's crazy. Oh. By induction of n, the result has already been established for n equals to 5. So assume n is greater or equal to 6 and let it be. Assume there exists h. Product of two transpositions and a contradiction equals blah 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 blah. And then I'll be done with chapter 4. So do I do chapter 5? Or maybe I'll do chapter 5. How long is chapter 5? Is chapter 5 hard? Please, chapter 5 don't be as hard as chapter 4. And then I'll be very sad. Oh, I'll be very sad. Chapter 5 seems okay. Chapter 5 seems okay. So, chapter 5 seems okay. The fundamental theorem of finitely generated abelian groups. A group is finitely generated if there is a finite subset A of G such that G is a subgroup generated by A. Okay, now for each R for each integer R, for each non-negative integer R, let ZR be blah blah blah. The free abelian group of rank R. Fuck me, bro. Proof. We shall derive this theorem in a later section. Which section? 12. Chapter 12. Let's check this section. By induction on n, the result has now been assume that n is greater or equal to 6 and let g is equal to an. Assume there exists a normal subgroup h in G where h is not equal to 1 on G. For each 1 to n, let Gi be the stabilizer of R in a natural action. Fuck you! What the fuck is a natural action? Left multiplication? Conjugation? Am I retarded? Oh no. Natural action on G on 1 to n. The natural action of G on I in 1 to n. That's stupid. Am I stupid? The stabilizer of I in the natural action. Okay, so G. So basically, G is acting on the set 1 to n. And how do you act on it? You apply the permutation on 1 to n. That's crazy. That's actually so crazy. How do you act on n? You know, what is an element of G? An element of G is an even permutation on n elements. So how do you naturally act on a set of n elements conveniently labeled 1 to n? You act on them by sending them to where your permutation will send it. That's crazy. So Gi is the stabilizer of I. And the stabilizer of I is isomorphic to an minus 1. Oh. What's that? Okay, that means that you don't move I. The even permutations in an which do not move I is isomorphic to an minus 1. Okay, fine, whatever, sure. How do you show it's isomorphic? You say it explicitly, you just map shit to shit, yeah? You map shit to shit. You map stuff to stuff. So by induction, Gi is simple for all I. Okay. For all I. For all I, Gi, the stabilizer is simple. How the fuck you write a book like this? This is so crazy. This is actually so crazy. How do you write a book like this? Oh.